Hi, I'm Lashan. I will present how to use abduction to learn from data with our improver. So we will deal with the natural language inference task, which is given the premise and the hypothesis and the code label, which says that there is a relation between premise and hypothesis. So this code label comes from the crowdsourcing, and the premise can be entailing the hypothesis, can be neutral towards the hypothesis or contradicting. Now, when we're talking about the reasoning with logic and deep learning, the perks what comes with the logic is that it can deal with a complex reasoning and their decisions are interpretable. On the other hand, deep learning methods can learn from data. They are robust, scalable, easy to deploy, and you don't need expert semanticists to develop your system. If logic-based systems knew how to learn lexical knowledge from the data, for example, puppy tells young dog or guitar and person and disjoint concepts, then this would balance the scale bit. So what is learning as abduction in a nutshell? So we have a problem, an inline problem, and there is an external knowledge base. The theorem prover tries to prove the problem given the knowledge retrieved from the knowledge base, but it fails. It says it's neutral, and code label says, on the other hand, that it should be a contradiction. Then the theorem proving is reversed, and it tries to find a relation which explains the contradiction label. Then it finds which is put on and removing disjoint. This learned knowledge is added to knowledge base, and now when we are theorem proving the same problem, we have all necessary knowledge and we can prove that it's contradiction. The research questions I'm trying to ask in this presentation is that what is the feasible way to learn from data via abduction, how to prevent learning of pseudo-knowledge, and whether the learning knowledge is enough or do we need some external knowledge base, and how does the learned knowledge boost performance. So let's introduce natural tableau. So it's a tableau system. The usual tableau systems are proof procedures, and they exist for many logics like model logic, first order logic, propositional, and so forth. Natural logic is the study of inference in natural language done as close as possible to surface forms. This is my favorite one-line description of natural logic. So natural tableau uses a version of natural logic which is a high order logic, and these are the high order terms, logical representations of the following sentences. And as you can see, we don't have these standard connectives there. So to show that a lark is in contradiction with every bird is flying, we use the inference rules which are in Tableau. So the inference rule is the following. So green means that it's true. So if it is true that an S is doing V, then we know that there is some individual C which is S and doing V. And if every S is doing V, then for any individual we know that either it's not S or it's doing V. And the rules has this intuition, is simple intuition behind it. So this is a closure rule which says that if A is X and A is not Y, but on the other hand I know from the knowledge base that X entails Y, then say that this doesn't make sense. So we start to prove this contradiction by searching a situation which makes both premise and hypothesis true. So from lark not moving, we get that there is an individual which is lark, and this it's true that it's not moving. From here we get that it is false that C is moving. From here we get rid of auxiliary and we get that it's false that C moves. Then every bird flying being true means that C is either is flying or it's not bird. So if it is not bird, at the same time we know that it's lark on the left branch, and this doesn't make sense based on the knowledge base. Therefore, this branch closes. And here C flying means that it's true that C flies. And here we also find a contradiction because C is not moving, but on the other hand it's flying. And based on the knowledge base, that doesn't make sense. So we close another branch, so all branches are closed, which means that we could not find a situation which makes both premise and hypothesis true. Therefore, it's a formal proof that premise contradicts hypothesis. So this is implemented in a LangPro, the natural language theorem prover, which uses very basic things, syntactic parser based on CCG and WordNet. So it parses sentences, then converts them into logical forms, and using WordNet and the theorem proving, it predicts the relation between premise and hypothesis. Now I will define what abductive reasoning is. So in logic, abductive reasoning is the following. We have a premise, and we would like to show that premise entails conclusion. So for that, we are searching for an explanation, that when we combine explanation with premise, then this will entail conclusion. Usually there are following constraints put on the explanation E. So it should be consistent with the premise, which means that if premise is lovely little puppy is sleeping, then explanation would be good if it is lovely and little are disjoint. This will make premise contradictory. Explanation should be minimal. So if I have puppy entails young dog and puppy entails dog as an explanation candidates, then second one is better because it has less information. And E has a predefined form. This means that if I have can be applied the form on the terms in the relation, so one might disprefer the very long relations. So learning as abduction works in the following way. So we have this previous example, but if we would substitute Lark with nestling, then we wouldn't be able to prove this problem because in the WordNet we don't have the relation nestling entails bird. So we would have right branch still closed, but the left one would be opened. And then we are searching the ways to close the left branch. So we are using in this case the closure rule, which we are applying in a backward way. So we are searching now the antecedents, and we have to find what relation they should satisfy. So in this case, there is two explanations how to close the left branch. One is nestling entailing bird, and another is nestling entailing move. So there can be several explanations per branch. So while this looks following, instead of one closure rule, we have additional 16 ones, and Tableau proofs are much longer. There are more open branches, and in each open branch can have several explanations to be closed. So for every closed branch, we pick at least one explanation, then in the end we will get an entire explanation for the entire Tableau. So that's a very huge explanation space. So we are shrinking them down severely, which means that we assume that branch-specific explanations should be shared all across all branches. So we take into account the intersection of all the explanations per branch. So the abductive workflow is the following. We have all the problems, and then theorem proving is proving them. The ones which are solved, we don't care. Unsolved ones will be reprocessed again. So the tableaus will be opened and is created, and they will be opened, obviously. And then abductive inference comes, where first we are filtering out those terms which doesn't meet the term shape. So we restrict the terms of size at most 3. Then we do a reverse proving, which means that we are extracting the possible explanations. The explanations which doesn't contain comparable terms in the relations are discarded. For example, puppy and little being disjoint will be discarded because part-of-speech text should be the same of the terms in the relation. The relations which are not consistent with knowledge base will be discarded. For example, lark and bird being disjoint will be discarded. We're checking the information amount. So if there is an explanation which contains too much information with respect to other one, we will prefer the one with less information. The relations which make sentences inconsistent will be discarded also, like toy and car being disjoint. Then we are checking, given all these relations, what are their impact on all problems in the data set. And we check whether they help to prove more problems or unsolve them. So the ones with good accuracy gain will be kept. And in the end, we are keeping those relations which has less terms inside. So all the collected knowledge will be put together, and this will be incorporated, added to the initial knowledge base, and the loop can be repeated again until we are not learning anything new. Now I will explain experiments and show the results. So for experiment, we use the SIG dataset because many logic-based systems were tested on this dataset. We use training set for threefold cross-validation and test set for final evaluation. We use also 3 different syzygy parsers and play with the rule application number in the theorem prover, whether it's set to 50 or 800. More rule applications gives better results, but it also takes more time. So when we compare two settings with 50 and 800 rule applications, we see that accurate difference in accuracy is very little. On the other hand, we decrease the CPU time almost 10 times. When we exclude the relations coming from WordNet, then we see that the accuracy goes down significantly, which means that WordNet still adds a value. So these are the results for LangPro on using different syzygy parsers. And when we use abduction, we see that the gain in accuracy is consistent across these different syzygy parsers. When we combine all 3 syzygy parsers, we get the best result. And when we add abduction to that system, we get still a gain improvement in the performance. And I would like to say that precision of the best system is pretty high, and this is very important when we are dealing with the logic-based systems, because logic-based systems are known to be reliable, so we would like their proofs to be as accurate as possible. We're comparing our results to the state-of-the-art in logic-based systems, so this belongs to syzygy2 lambda when it is used with phrase-to-phrase abduction. And as we can see, while the results are comparable, their precision suffers much when it hits the state-of-the-art, while in our case we still maintain very high precision. I would like to say that using abduction is common in linguistic semantics. There's a seminal work where they use interpretation of a sentence in a context, and also abductive reasoning was successfully applied in the very first year task on RTE. So let's see what kind of knowledge is learned. So in total, there's 312 relations learned based on the 1000 unsolved problems, which were supposed to be proved. So these are my annotation of those relations, and here you see the distribution of correct, wrong, contextual, and reversed relations. So these relations are evaluated out of the context. So here is the wrong entailment, star entails sky. So in this example, in this context, is correct, but most of the cases this relation is wrong, so that's why it's wrong, classified as a wrong knowledge. Writing and get are not contradictory, but if we would add more context, like writing in and getting out of, then it's really a contradiction. In entails at is correct in many cases, but in many other cases it's not, so it's highly contextual. Cap entailing het is also contextual, but in this particular example, it very well explains why premise should entail hypothesis. Person entailing man is a wrong direction of the entailment, but this is due to the gender bias reflected in the code label. There is also a noisy label which makes the abduction to learn that dog entails bulldog. And this is the correct knowledge learned that acrobatics entails trick, which explains this entailment. And lying down and around being contradictions is an explanation that a squirrel is lying down contradicts a squirrel is running around in circles. To conclude, I would like to answer a research question I posed in the very beginning. So we achieved a computationally feasible way to learn knowledge from data via abduction, and we did this by reducing the explanation space and applying the filters to the explanations. We could not entirely prevent all pseudo knowledge, but the ones which leaked did not harm the performance in the end. As we saw, WordNet still adds an important gain to the performance to hit the state of the art, so we cannot replace it with the learned knowledge. And as we have seen, abduction helps to consistently increase accuracy across all syzygy parsers we considered, and while doing so, we still maintain a high precision. Thank you for listening, and see you at the conference.